Hello students, I hope you all are doing well. So we'll continue with the chapter chemical kinetics. So in this video, we'll start a new topic, that is integrated rate law equation. So in this topic, you have to derive an equation for zero order reaction and first order reaction. You have to derive a differential equation. So to start with, we'll take zero order reaction. So first, let us consider a reaction R to P, where R is reactant and P is product. Say at time t equal to 0, the concentration of reactant is R0. And at time t, at any given time t, the concentration of reactant is RT. Now, we'll apply here the concept of rate law and integrated rate equation. So first, according to rate law equation, the rate of this reaction is equal to rate constant multiplied by concentration of reactant, that is R. Now since this is a zero order reaction, we'll have R to the power 0. So we can write K, R to the power 0 is equal to 1. So rate of a reaction is equal to K. This is according to rate law equation. Next, according to integrated rate of reaction, rate of a reaction is equal to minus dr by dt. In integrated rate of chemical reaction, we represent the change of concentration of reactant and time in differential form. So let this be equation number 2. Now you can see in equation 1 and 2, the left hand side is same. So if we compare equation 1 and 2, we can write minus dr by dt is equal to K. In the next step, we'll separate the variables. So what are the variables here? R, that is reactant, and time t. So we'll separate the variables. Minus dr equal to K dt. Next, we'll do integration. Integration of reactant dr from concentration of reactant R0 to RT is equal to integration of K dt from 0 to T. So when the time is 0, concentration of reactant is R0. When time is T, concentration of reactant is RT. So next, minus R0 to RT dr is equal to, K is constant, so constant will come out, 0 to T, that is dt. Now we know integration of dx is equal to x. So therefore integration of dr is equal to r. Limit from R0 to RT is equal to K. Integration of dt is t from 0 to t plus integration constant c. So we'll put the value of the limits. So first r equal to RT, that is upper limit, minus r is equal to R0, that is lower limit, is equal to K, t equal to t minus t equal to 0. So t minus 0 plus integration constant C. So if you multiply by the negative sign, you will get R0 minus RT is equal to KT plus C. Here R0 is the concentration of reactant at time t equal to 0. RT is the concentration of reactant at time t. K is rate constant. T is time. And C is integration constant. So in the next step, what we do, we try to remove the integration constant C from the equation. When time t is equal to 0, RT is equal to R0. So if you put these values, if you substitute in equation 3, we'll get R0 minus R0 equal to K multiplied by 0 plus C. So from here we'll get C equal to 0. So we'll put C equal to 0 in equation 3. So from equation 3 we get R0 minus RT is equal to KT. So this is the integrated rate equation for zero order reaction. Next, from here we'll derive the half-life time period for zero order. Half-life. Half-life is the time period in which half of the reactant is converted to product. Say for example you have A as reactant, B is product, and at time t equal to 0, say you have 10 gram. So half of the reactant will be 5 gram. So the time which is required to convert the half of the initial concentration of reactant to product is known as half-life time. So half-life, when time t is equal to t half, that is half-life time, R0, then RT is half of R0. So if you substitute this in this equation, that is integrated rate law equation for zero order, we'll get R0 minus half of R0 equal to KT half, which implies R0 minus half of R0 is half R0 equal to KT half. So this is the half-life equation for zero order reaction. Next, we'll derive integrated rate equation for first order reaction. So again, let us take a reaction R to P, where R is reactant, P is product. So when time t equal to 0, let the concentration of reactant be R0. When time t, let the concentration of reactant be RT. So again, from rate law equation, we get rate is equal to rate constant multiplied by concentration of reactant. Now since this is first order reaction, the order of the reaction is 1. So we'll write here 1. So we can write rate is equal to KR. Let this be equation 1. Again, from integrated rate of chemical reaction, we get rate is equal to minus dr by dt. This is equation 2. So from equation 1 and 2, Left hand side is same, so we'll equate the right hand side. We get minus dr by dt equal to kt. In the next step, we'll separate the variable. So we'll write minus dr by r is equal to k dt. Next step, we'll do integration. So integration of dr by r, limit r0 to rt is equal to integration of k dt from 0 to t. Next, we know integration of dx is equal to x. Integration of dx by x is equal to log x. In math, here we'll use ln of x. So integration of dr by r is ln of r from r0 to rt is equal to k is constant, will come out. Integration of dt is t from 0 to t plus integration constant c. Let us put the limit. So minus ln of rt minus ln of r0 is equal to k t minus 0 plus c. So if you multiply by this negative sign, you will get ln of r0 by rt, ln of r0 minus ln of rt is equal to kt plus c. Now when time t is equal to 0, concentration of reactant rt is equal to r0. So if you substitute this value in the third equation, that is equation 3, we'll get ln of r0 minus ln of r0 equal to k multiplied by 0 plus c. So from here you'll get c equal to 0. So if you substitute c equal to 0 in equation 3, we get ln of r0 minus ln of rt is equal to kt. Or we can write ln of r0 by rt is equal to kt. Because we know this formula, ln of a minus ln of b is equal to ln of a by b. So this is the integrated rate equation for first order reaction. Next, let us derive the integrated rate equation for half-life in first order reaction. So when time t is equal to t half, that is half-life, concentration of reactant RT is equal to half of R0. So if we substitute this in the final equation, that is equation for rate law in first order, you'll get ln of R0 by half of R0 is equal to K multiplied by T half. Now we can convert ln in terms of log. So ln equal to 2.303 log R0 by R0 multiplied by 2. So R0 cancel. So you'll get 2.303 multiplied by log 2 is equal to K T half. The value of log 2 is 0.301. So if you multiply 2.303 by 0.301, you'll get 0.693 is equal to K T half. So this is the half-life equation for first order reaction. So thank you. In the next class, we'll do a numerical based on these formulas.